All right. Well, let's get started as people are still joining, and we have an action-packed hour here. I'm really excited about it. Cooking with gas is a big topic now. It's not only a lot of interesting sciences occurring, a lot of innovation in cooking products, but it's also become a political hot potato. So we're gonna face it head on. Let me do a quick introduction to our two speakers, and so they can jump in. Our first speaker is Brady Seals, and she's the manager of RMI's Carbon-Free Buildings Program, driving the narrative on health and air quality benefits of electrifying buildings, including developing the network of health experts and advocates across the country who advance health and climate policy. Brady and her team's work focuses on gas and induction stoves, retrofitting HVAC in schools for student health and learning, indoor air quality guidelines, and the health benefits of whole home retrofits. Previously, she has a decade of experience within the global household energy sector, has worked as a consultant advising nonprofits, corporations, and multinationals on energy impact strategies and investments in over 16 countries, as well as supported the World Bank's 2020 report, The State of Access to Modern Energy Cooking Services. Welcome, Brady. So glad you can make it. And let me also introduce Rob Jackson, who is a professor at Earth System Sciences at Doerr School of Sustainability here at Stanford, and a fellow at Stanford's Woods Institute for the Environment. He and his lab examine the many ways people affect the Earth. They seek basic scientific knowledge and use it to help shape policies and reduce the environmental footprint of global warming, energy extraction, and other issues. They are also working to measure and reduce greenhouse gas emissions through the Global Carbon Project, which Jackson chairs. Among numerous books he has written on the environment, is his upcoming book this July titled Into the Clear Blue Sky, The Path to Restoring Our Atmosphere. So welcome, Rob. So we have two very experienced individuals in this area who are very much on top of the latest science and policy. So thank you both for joining us, and I'll hand it over to Brady.
Thanks, Peter and Lindsay, and to all of you. I see some familiar names in the panelist and participant list, and some new ones. So excited to be here with you all. Well, great. So we are here today to talk about gas stoves, which happen to be inside of our buildings, inside of our homes. As Peter said, I'm on RMI's Carbon-Free Buildings program. So we spend a lot of time thinking about the climate and energy impacts of buildings and how we can electrify the 70 million buildings that still burn fossil fuels and make them efficient, and so that they become better for our health and better for climate. But today we'll be talking a lot about indoor air quality. So the appliance that comes to mind is gas stoves. And I just wanted to share this first chart to give some level setting about how many gas stoves are we really talking about. And as you can see from this map, gas stove use really varies depending on where you live. So if you are feeling up for it, drop in what state, or if you're international, where you're calling in from. Be fun to see. If you're affiliated with an organization or a university, feel free to drop that in too, just to see where everyone's calling in from. But essentially, the interesting thing I want you to look at first is that most of us are actually already cooking with electric stoves. So a little over a third of the US cooks with gas. The national average, and this is from 2020 numbers, is about 38%. But that can change a lot depending on where you are. So if any of you are calling in from California, about 70% of Californians currently cook with gas. Compare that to the South, where It's already very electrified. So for example, Florida, only 8% of homes cook with gas. So this is, I think, a helpful framing to keep in mind. And when you look at this map, the darker color means the greater share of cooking with gas, and the lighter color is the less homes cooking with gas. So that's a bit of a grounding. And then I just have 2 slides for you. And I'm gonna try to make a somewhat complicated issue as simple as I can. And then Rob will take us through some of the exciting research happening now. But so first up, what is the problem with gas stoves? Also, why is RMI working on gas stoves? We're a climate and energy nonprofit that's been around for 40 years. So we realize that in all other sectors, transport, industry, you name it, electricity generation, emissions had been going down. Virtually the only sector where there was no progress on our carbon emissions was buildings. Buildings have been flat. And a stat from the gas industry is that a new consumer is hooked up to the gas infrastructure every minute. So we're going flat and then also in the wrong direction from a climate perspective. So when we think about our homes and our commercial buildings, the big climate polluters are usually in our basements, and there are furnaces and our boilers that have a big climate impact outside. Stoves have a much smaller share of the carbon emissions. But when we started to talk to people, researchers, academics, they said, yes, but there's this outsized health impact because we live and breathe around our gas stoves. So we got into this because we were hearing about this from advocates, academics, and we wanted to try and synthesize the issue. So in 2020, when we started going into it, we came up with a summary study and have done work since then. But I just wanted to highlight 6 main points of why gas stoves are an overlooked health concern. And the first up is that the most basic gas stoves, they release some similar pollutants that come from our cars, which we know is bad for our health, but we don't have the same sense of our gas stoves. And Rob will talk more about this, but essentially gas stoves are bad for health because they release pollutants. And there's actually been about 50 years of health studies going back to the 70s that look at the risk of cooking with gas. Now, most of these studies are epidemiological studies that are focused on specific pollutants like nitrogen dioxide and the associated asthma risk. And we have studies spanning several countries in Europe, the US, and a few studies internationally. In the last few years, there's been a big flurry of studies with a lot of excitement around getting new data. And I think what we're finding is that pretty much for the last 50 years, we've been finding the same things, that these pollutants are bad for our health. Now we just know how bad these pollutants are. And Rob and his team, as they're finding there's more pollutants than we maybe knew about before. Another issue is that the gas stove doesn't come with a built-in protection. So right now, if you have a gas stove or range, kind of use those words interchangeably, you may or may not have ventilation, a range hood over the top. So that would be our one protection that could be built into the gas stove, but it's sold separately. And so unfortunately, there's really 3 main issues with ventilation. One, many people don't have it. Unfortunately, there's no data set that shows us how many people have ventilation, but we know because building codes can vary from local regions and state regions that many people just don't have ventilation. Second, you may have inadequate ventilation. I have a range hood in my microwave that simply recirculates the air. Is not very effective, doesn't even cover the whole part of my stove. And then third, and maybe most importantly, we see time and time again that people don't use their range hoods. I myself would be in this guilty category before I knew some of these health homes, and really only ever turned on my range hood when I was burning something. And then I think a big next step is that gas stove pollution, like many exposures, is very inequitable. So there are a number of factors why lower income households and people of color may be disproportionately exposed to gas stove pollution. A couple factors are living in smaller homes with more people, already living closer to other sources of pollution has a cumulative effect. And we know from the research that one of the challenges is if you already have asthma or a respiratory illness, exposure to gas stove pollution can actually exacerbate some of those issues. We have seen that children are also one of the populations that are most affected by this. So one of the stats that I'll share with you, which is from a meta-analysis that looks at all the studies and tries to find the similarities, is that children who live in a home with a gas stove have a 42% increased risk of having asthma symptoms. So that's what's defined as current asthma. Lifetime asthma, which they define as being diagnosed by asthma with a doctor, is about 24%. So we know that children are particularly vulnerable to this kind of gas stove pollution. I will also say that Lawrence Berkeley National Lab just released a new study where they looked at this data again to see if these numbers were in line, and they found that it did. So there's this huge body of research which is pretty consistent with its findings. Then finally, one of the things that we did here at RMI was we knew clearly gas stoves are bad, but we didn't have a good sense of how bad. So we did a study last year where we tried to calculate what is the population level risk for gas stoves. And essentially we found that, you remember that math in the beginning, 38% of households with gas stoves. And then we looked at households with children with gas stoves, and we calculated that about 12.7% of childhood asthma in the US could be linked to gas stoves. And in some states like California, Illinois, New York, where gas stove prevalence is much higher, those numbers could be more like 20%. And so that risk, that 12.7, the calculation is called a population attributable fraction. That's actually similar to a child's asthma risk of living with a smoker. So all this to say, before a couple of years ago, many of us hadn't thought about gas stove pollution, but now from the evidence, which is not really that new, there's new frontiers of the research, which is adding to this great body and helping us find new things. But there's a long history where we know that it's bad, and now we're starting to quantify that and put some finer points on it. So with that, RMI, we are promoting all electric efficient buildings, and how can that help? How could this help solve some of the problems with gas stove pollution? And at the most basic, again, contrasting from the last slide, by taking out a gas stove and putting in an electric or electric induction stove, we essentially can eliminate combustion pollutants like nitrogen dioxide and carbon monoxide. So all of a sudden, those go down to zero. Rob will talk about this, I'm sure, but it also eliminates other risks like benzene. And this is this new frontier of research, which is adding to this long history, 50 years of studies. We get this question a lot. Well, what about food? Cooking food releases pollutants, and that's true. It does. Pollutants like particulate matter. But we find that the best solution to reduce exposure is electric or induction, so zero combustion pollutants, and then effective ventilation that reaches outdoors, that is powerful enough to help remove some of those pollutants. Finally, in induction stoves are a lot safer, so it's a bit hard to see on the picture in the bottom left, but induction stoves only heat up when the pot is on it. So you can see the butter that's melting, and then the pat of butter that's just on the stovetop itself is staying cool. And you'll see often people put their hand down, or my first time seeing an induction demonstration, someone put $100 bill underneath their stove and turned it on. So the surface area stays cool. And then there's a lot of things harder to measure, but why people want to change and want to move. And those are things like they're much easier to clean. So we know that building electrification is important for climate and health goals, but not always easy because of many challenges. And so we both need policies to help us get there, but we also need people to want to make the change. And so induction offers some of these other co-benefits. Finally, I think resilience is a big topic here. What happens when the power goes out? And there are efforts underway where stoves are actually being developed with batteries, and also with this kind of ease of retrofitting with 120 volt instead of having to upgrade your outlet near your stove. So I know it's a lot. I'm hoping we can dig in more in the discussion, and you're in for a treat with Rob's presentation, but hopefully this was a helpful framing of the challenges with gas stoves and some of the benefits we see by going electric in the kitchen.
All right, just interject here for a half second. We'll take the questions at the end. You feel free to type the questions into the chat or save them and we can unmute you. Rob, go, and then we'll jump into all the questions. Thank you.
Well, thank you all for being here. It's always a pleasure to work with Brady and RMI. I'm Rob Jackson from Stanford. And I want to begin by acknowledging our partners in this work. We've been working for a number of years now with PSE Healthy Energy. The paper that's publishing tomorrow is with the Harvard T.H. Chan School of Public Health, Dr. Kari Nadeau. And also we have a long-term relationship with the Central California Asthma Collaborative. They help us find homes, and they serve households with children with asthma, and we work to measure pollution in their homes and try and reduce it. So thank you to all of our partners and for you being here. I'm talking today just about gas and propane stoves, a general overview, and with an emphasis on some of our recent findings. There is 50 years of research on this field, particularly when you look at nitrogen dioxide, but there are still new things that we're learning and other people are learning, all of which reinforce the direction of moving towards electric induction. Let me begin by providing my lens. I came to work on homes and buildings as the chair of the Global Carbon Project. We track greenhouse gas emissions around the world, carbon dioxide, methane, nitrous oxide, and about to come out hydrogen. So we measure all human sources, we measure natural sources, and try and put those things together from bottom-up tools and also from the atmosphere on down. So I come at this work originally from a climate lens, trying to quantify methane emissions. But as we kept studying buildings, which were the least understood part of the methane cycle, we began to measure indoor pollutants because we were entering hundreds of homes. And I was surprised, frankly, to see the levels of pollution that we were finding and how quickly they rose to the dangerous levels in some cases. And one more slide for background. Brady kind of alluded to this. Our air is better today, cleaner than when I was a boy, and that's something to celebrate. We have not made similar progress at cleaning up our indoor air. But even in spite of the benefits in the cleaner air that we breathe today, there are 100,000 Americans who are still killed every year by coal and car pollution, particulates in particular. There are 10 million people around the world who die of fossil fuel pollution. That's 1 in 5 deaths. So we have a lot of work to do, having made progress to date, and we can save lives and make all of ourselves healthier while we also fix the climate problem. Some relevant past and ongoing research. I'll talk about ours mostly today, but I want to acknowledge other things that are happening. There's the CLASP project. You can see that at the top. This is in Europe, clearing the air, gas cooking and pollution in European homes. This is an ongoing study where they're visiting homes and taking measurements. They just came out with a report about 6 months ago. It's worth a read. The Canadian child cohort study, I believe, led by Michael Brower. They're tracking thousands of kids and households for asthma and different health outcomes. Also another one to keep an eye on. And then, of course, Brady and RMI's work that she referred to, looking at relationships between the prevalence and presence of gas stoves and occurrence of asthma. So there's a lot to look at. And she mentioned the 50 years of research. Just to put that in perspective, there was a meta-analysis of dozens of studies done in the 1990s showing links between gas stove use and nitrogen dioxide pollution. So it's not as if this is something that we don't know about or don't understand. We've known this for decades, and yet it's still hard to decarbonize our homes. So let me turn for the rest of the time to our work. This is just a rundown of a few relevant papers. 2 years ago, we published a paper led by Eric Labelle. You can see the one at the top, quantifying methane emissions and NOx emissions from gas stoves, cooktops, and ovens. We also have published papers on water heaters and other gas appliances in homes. But the methane emissions that we found just from the piping in our homes and our appliances was equivalent on the yearly basis to the pollution from 500,000 American vehicles. And that does not include the methane that's leaking out from supply to the house. And it does not include the carbon dioxide emissions that are coming from burning gas as a fossil fuel. We also found substantial amounts of NOx emissions, and I'll build on that result today. Last summer, Aminai Kashtan, a PhD student in our group, published the first study to quantify benzene emissions from gas stoves. They were substantial. There's zero from electric, but substantial from gas and propane. And then a paper from Cheng Hao that just came out last fall, Cheng Hao Wong. This one's not directly relevant to air quality, but is important because it allows us, using federal data, to estimate the amount of gas burned in homes, essentially by zip code. So that if we think about scaling results for pollution, nitrogen dioxide per joule of gas burned, knowing how much gas houses are consuming allows us to say something about the likely health impact in those places. And then most recently, and not even out yet, this paper at the bottom will be out tomorrow. Tomorrow is World Asthma Day. I'd be surprised if many or any of you knew that. But this paper is new in providing a US-based estimate of exposure to nitrogen dioxide stratified by socioeconomic groups, poorer communities, racial and ethnic groups. It also tracks nitrogen dioxide pollution throughout the home to bedrooms and other places. And as Brady mentioned, we know that poor people breathe dirtier air outdoors. And what we're finding through studies like this is they breathe dirtier air indoors too. And we can quantify how much that is. So these are some pictures just to give you an idea of what we do when we go in a home. On the left, that's Colin Finnegan from our group. That's a home in Bakersfield. You might note there's no range hood in that kitchen. And you might also note the pot of boiling water. All the measurements that we take, we use the same pot. We just boil water. We do not cook food unless we are testing emissions from food. So that the only pollution that we're seeing or measuring is from the flame, from the fuel itself. On the right, you see the instruments. So we have benzene instruments, the big green one at the bottom, NOx gases on top of it, carbon monoxide, methane, ethane, just a whole host of gases. This is expensive, painstaking, and time-consuming work. To do 50 or 100 homes is months to years of work. Finding homeowners, taking measurements. If you want to do long time courses, say 8 hours or most of a day, we sometimes rent Airbnb homes because we enter your home at 8 in the morning and most people don't want us still sitting around at 9 o'clock at night. So we track these kinds of measurements now in hundreds of homes. Let's begin just with what we see. Let's not worry about what this means yet. I just want to give you some intuition about how we know what we know. You're looking at a time course on the x-axis, and then on the y-axis is an arbitrary concentration. It's arbitrary. I'm not hiding anything. It's just that we've made them all relative to 1 to fit on the same graph. So let's start with carbon dioxide, the bluish one in the middle. You see that carbon dioxide is flat. White is baseline starting. The bar in the middle, steady state off, is before the gas stove turns on. And for carbon dioxide, you see that line is completely flat. That makes sense because there's no combustion happening at that time. This is in the kitchen. Then there's a brief period before we turn it on where it wiggles up a little bit. That is you're seeing the breath of the person walking into the kitchen to arrange the pot and the measurements. So we pick that up with our analyzers. Then you turn the stove on and you see this steep peak for rise in carbon dioxide until the stove is turned off. And it rises linearly, and that's as a function of the amount of gas burned. When you turn the stove off, the CO2 concentration is flat. For NOx gas below that in green, you see a pretty similar thing, except there's no NOx from our breath, so that line stays flat. You turn the burner on, and then boom, it's straight like a line again. Turn the burner off, it goes off. That's the source of pollution indoors. It's a linear relationship with the amount of gas burned. So we can predict how much pollution will enter a home if you tell us how much gas is being burned in that home. But it's different for methane. Look at the purple one on top. Methane isn't flat when the stove is off, right? It's not rising quickly, but it is rising steadily. That's methane leaking out of pipelines, fittings in the kitchen. That's the greenhouse gas effect of just simply having gas hookups in 40 or 50 million buildings or more. So you don't see that for CO2, you don't see it for NOx, but methane leaks all the time. It leaks a lot when you turn the burner on. That's the puff of unburned gas that happens when you first flip the burner. It's flat when mostly flat when the stove is on. There's some uncombusted methane. There's also a little bit of methane that's consumed in the flame. You turn that burner off again, there's another puff because there's a delay in time between the gas being off and unburned gas entering the room. So this is a typology of the kind of thing we see. All right, first result is that the fuel choice dictates indoor air pollution. It's the flame, the fuel, but it's really the flame and not the food for benzene that we published last year and for nitrogen dioxide. And I say this in two figures you're seeing here, benzene on the left, NO2 on the right. These are burners from a stove. The orange and whatever color that is, brownish one, are gas and propane. You see they are substantial. These numbers don't tell you what they mean health-wise yet, but they just say those fuels emit these pollutants. And you see the two electric fuels to the left, the red dots, are indistinguishable from zero. So electric induction and coil emits zero benzene and zero nitrogen dioxide. It's strictly about the fuel. So you can reduce your exposure to pollution by switching out a gas or propane fossil fuel appliance for electric, and you'll be safer by doing so. And it's quite clear, there's absolutely no doubt that this is the case. That result makes perfect sense if you know anything about NOx gases, right? NOx gases form at very high temperatures in air, close to 3,000 degrees. They form in open flames, they form in refineries, they form in lightning, they form in cars. That's why we have catalytic converters on our cars, because the fuel, the gasoline that burns at very high temperature, generates NOx. The same thing happens in our homes, but an electric stove doesn't heat a very large parcel of air, and it doesn't heat it nearly as much as an open gas flame does. That's why it's zero for electric and high for fossil. Okay, not only do the stoves emit nitrogen dioxide and benzene, but that pollution travels throughout the home. And this is one of the areas that I think is a new frontier. We're trying to understand how much people actually breathe. These are 6 houses you're looking at here for NO2 as a time course. These are 8-hour time courses. We turn the stove on near zero there. You see the baseline measurement. We turn the stove on. NO2 starts to jump immediately, not surprisingly. For 3 of these houses, it gets above the World Health Organization and the EPA 1-hour health guideline within about half an hour. So the pollution doesn't stay in the kitchen. It's worse in the kitchen, of course, but it doesn't stay in the kitchen. That hot, buoyant air moves throughout the home very quickly. In some cases, and these are all bedrooms that are farthest from the kitchen down the hall, it gets to dangerous levels in living rooms where other people are sitting. Even for the other 3 houses with these long time courses, you see they all go up. They don't quite cross that 1-hour health guideline, but they all are above the WHO chronic health exposure guideline. So we know the pollution comes from the stoves, but we're just really beginning to understand how quickly, how far, and how fast it moves into our homes. True for propane and gas both. Same is true for benzene, a similar story. In this case, one of the houses jumps above 8 ppb. That's the acute REL. That is really, really dangerous. You do not want to be breathing benzene at those sorts of levels. And benzene is a little different than NOx gases. There is no safe level of benzene. Every additional increment is dangerous to us, the doctors tell us. So again, here, 3 houses, you're above the 8-hour standard, and in one case above the acute standard. 3 houses, you're below it, but even in those ones where you're, quote, below, you're still adding extra benzene into the air of these homes, and it stays there for hours, right? You have to think about this time course happening, what, twice a day? We cook at lunch, perhaps, or breakfast. We cook again in dinner. These pollutants linger in our air for hours. You cook again later in the day, and you cook hundreds of days a year. So this cycle is repeating itself over and over as we go through a typical year. That's where the exposure and the extra asthma and health outcomes comes from. All right, why can't we just turn our hoods on? And clearly ventilation helps, right? You can turn a hood on, you can open your window, but turning hoods on doesn't help always very much. It helps sometimes, and sometimes only a little bit. First of all, surveys show that most people don't use their hoods. Less than a third of people do typically. They're loud, they're noisy, they're inconvenient. But even when we do use them, like the house on the left, you see it does help to lower concentrations a bit. So hood on is the orange circles, hood off is the orange stars. So you see those concentrations come down a little bit. However, even with the hood on, this house is above the 8-hour REL, the recommended exposure limit for benzene. So it helps, but these people are still at risk. And if you think the hood is protecting you from the benzene pollution, it's not. Then the house on the right shows a house where the concentrations didn't reach as high. The benzene emission rate wasn't quite so high, but the hood does nothing. There's no difference between the two traces, hood on, hood off. So we really can't rely on hoods to solve this problem. If you have a really high, almost commercial grade hood, and if you use it all the time, like a 75% capture hood, it helps a lot. But most of us don't have those hoods. They're loud. And the only way we can eliminate this pollution is simply to switch the fuel. This is a study that we're underway, and this is our work with PSC Healthy Energy and other partners. We've been measuring hoods outside of California. We've been to Colorado, Houston, New York City, Washington, D.C. In the study that's coming out tomorrow, where we measured NO2 and benzene pollution. You see the picture on the right. That's in Shanghai. We were in Shanghai, China, in December, and this is really labor intensive work, and it's difficult to do. But there are some differences that we find with stoves in some cities, particularly in China. They cook on very high temperatures, tend to have larger burners. They also have higher power hoods. Human behavior matters. In China, if you're cooking noodles or cooking rice, boiling water, they tend not to use their hoods because they don't perceive that the flame is the source of danger. They think about the oils in the food cooking, but the flame is dangerous. And people in China tend to close their doors when they cook, which confines the space and the airflow. That's better for people elsewhere in the home, but worse for cooks standing there. So part of this work is to understand differences in stoves, gas supply, and human behavior too. This is ongoing work. But as that last picture showed you with all those instruments and all those people, we will never have enough time and money to sample all of the variables we need. You can have burners on high, on low, windows open, closed, hoods on, off, cooking multiple burners in the oven at the same time, opening a window depending on the weather. There are too many variables, and we have to use models to help us understand risk. So we're currently using the CONTAM model. This is a well-used NIST model that propagates airflow through a home. And we combine that CONTAM model with our in-home measurements for pollution. And REX is a federal or a national kind of behavioral and energy database that helps us understand things like window opening and lots of other variables that you see here. It has data for standard home sizes. First principles would tell you that people living in smaller homes are more at risk than people in larger homes because the same pollution is diluted over a smaller volume. We have data from REX on range hood quality and use. You have to think about who's the cook. The cook is the person experiencing the most risk, although as I've already showed you, the pollution travels. Weather matters because if it's 115 degrees in Bakersfield, like summer days we sampled, no one opens their window, and the Bakersfield air outdoors is the worst in the country anyway. So they have extra pollution outdoors, and they have it indoors as well. So we put all of these things together in a model to try and look at different scenarios. This is the kind of thing we look at. We have about 20 homes where we have taken measurements, used the model to predict what the concentrations would be. The model traces in blue based on the house size and other measurements that we make, and our data are in black. This house shows quite good agreement. between the measured and modeled. Not every home is this good. We have about 20, but in general, the measurements and the model map onto each other quite well and give us a lot of confidence that the model results are valid. Well, so in terms of summary, and I'll stop, I mean, fuel choice and how much gas you burn are the most important factors for predicting exposure. They're more important than whether you use a hood, whether you use a window opening or anything else. Hoods help, as I mentioned, but they don't eliminate risk, and we shouldn't rely on them to do that. And people generally don't use them typically anyway. And then benzene and nitrogen dioxide exposures from gas stove use, as I've shown you, in concentrations that people are breathing in real homes, not in test kitchens, they often exceed national and international health benchmarks. So the pollution generated by stoves is substantial. It moves through our homes quickly, and it's dangerous. Peter was kind enough to mention my book. Let me put a shameless plug for my book up on the screen. This is coming out in July 30th. It's an optimistic view of climate solutions. I visit people around the world working to reduce greenhouse gas emissions and include some of my own work. I have a chapter on gas stoves and pollution. So thank you everyone for attending, and thank you for your work. And I'll stop.
Fantastic.
I'll stop
Yeah,
sharing.
thank you. Okay, great. Thank you, Rob. As an engineer, I love seeing the data. So in God we trust, all others bring data, please. Great. So I'd like to open it up for questions. There is one here. Do you find that the price or age of the gas stove correlates with the amount of pollution produced and fugitive methane leaked?
I can take a stab, and we'll have to tag team with Brady and others. The answer, surprisingly, is no. So we don't see any evidence that older stoves pollute more, or maybe put differently, you might expect that newer stoves are somehow more efficient and pollute less, and that is not the case based on our sampling. What does affect the stoves is how dirty they are. So benzene and carbon monoxide are what we call partial combustion products. It's when the mix of fuel to oxygen isn't quite right, those are formed. And in some cases, stoves that are very dirty, we think tend to combust less efficiently. But in general, buying a new stove does nothing to solve the problems we talked about if it's gas. It only helps if it's electric.
Yeah, and the only thing I would add is that pilot lights were actually outlawed on stoves by the Consumer Product Safety Commission, I think in the 90s. Gosh, I think it was in the 90s. However, many people have stories of stoves still burning pilot lights, older stoves in their homes. I'm from New York originally, and I have many friends living in New York City apartments with 4 pilot lights on. And we know from the old research that each pilot light adds about 10 parts per billion of NO2. I'm not sure, Rob, if you've encountered any old pilot light stoves. So I would say that's one thing. If you have an older stove with a pilot light, something to maybe consider. Additionally, some folks are turning their gas stove into a bit of an induction stove by putting like cookie pans on top or a big butcher block, and then getting a plug-in induction stove and putting that on and using that. And so one thing to note is just to be careful of doing that if there is a pilot light still happening. So that's the only thing I would add.
And Brady's absolutely right. We do see, especially that there are certain brands of stoves that are like Mustangs for car buffs, like Wedgwood and Wolf. People are very attached to them, and they do have pilot lights. We see them often in commercial kitchens too. You really do not want a stove with a pilot light in your home. Brady's absolutely right. They also leak the most methane when we take measurements. So yeah, you should switch.
There's one question, and then also a hand up. So I asked you to unmute, Jessica, but there's one real quick from Jordan. I rent an apartment in San Francisco. Is there legislation I can reference to encourage our landlord to replace our gas stove with induction?
you want me to answer, Brady, or would you like to take a first stab?
You go first, I'll go after.
There was, so there were a series of REACH codes that were passed over the last couple of years to require new construction be electric. There isn't a piece of legislation anywhere in the country that requires someone to replace a functioning gas stove that I know of. There are laws, particularly in states like New York, where future purchases must be electric. There is AB 32, our climate bill, I think it was 32 in California, encourages reductions or mandates reductions in greenhouse gases. Ultimately, those bills will reduce the prevalence of gas stoves in our state. Now, there's also a AB 2513 in the legislature currently, which is a labeling bill for gas stoves. I testified in the California House committee a couple weeks ago. That bill has moved from committee to the full legislature. I don't know the state, but it specifically mentions benzene, nitrogen dioxide, and carbon monoxide as being emitted by gas stoves. I don't know if that would do anything to your landlord, but there's no way to require a landlord to replace a gas stove that I know of.
Yeah, I would just say thanks for bringing up this question. It highlights, I think, one of the biggest challenges to this, which is we know that often renters are people who may be disproportionately affected by this. And it's the question of split incentives for property owners and for renters. I will say that being in San Francisco, there are changes to the energy code, the statewide energy code, that you might be able to reference when it comes to ventilation. For the first time ever, California required heavier ventilation if you have a gas stove versus an electric stove. But again, this is unfortunately most of the laws that we have besides Berkeley are for new construction. But I think that there could be some things for you, especially since you're in San Francisco, California, based on where policies are heading. And I do think it's very likely in some of the future state energy codes that we will see some more requirements when it comes to retrofits. So I will drop a few links in the chat, but unfortunately nothing perfect yet. But at the very least, maybe the landlord could front the cost of a portable induction stove, and I can drop into the chat one of the models that's often on the top of Wirecutter and highly rated that many of us use when we can't make the choice ourselves to switch our stove.
Sorry for jumping back in. Brady's absolutely right. That's a terrific point. These benchtop induction units are sort of $50 to $100. They work very well, and we recommend them in areas like Bakersfield where it's so hot in summer that residents can't open their windows. It may be that the IRA, the Inflation Reduction Act, incentives could apply to your landlord. I would encourage them to look at that. There are incentives for electrification, and I should know what those are for someone in San Francisco, but I don't remember. So check out the IRA incentives.
Jessica, do you want to ask your question?
Yes, thank you so much, Lindsay. Thank you so much, Rob and Brady, for sharing all that information. I love the graphs. I'm curious. So the first map, I was really struck by the difference between gas stove use across the country and how actually a lot of people already do cook on electric. However, I live in California, and whenever you bring up electric or induction, it gets very emotional. And so I'm curious why you think there's this discrepancy. Most of the country does cook on electric. So I'm curious about the emotions you encounter in your work when you're presenting your data, and any ideas of how to approach the public when you're doing so.
Okay, I love this question because I hear a lot, people love gas stoves. Everyone loves their gas stove, but is that really true? And so going back to the data, there is polling that shows that not everyone loves their gas stove. People love what they know. So when you ask people, and the survey results have showed this, if you have an electric stove and, they prefer electric, but if you have gas, you prefer gas. And so, you know, there's been obviously a lot of marketing to get us to love and keep these products in our home. But I think some of this polling, and I can also look for that and drop it in to say, actually what we find is that people seem to like what they know. And so part of the problem is that induction is less than 5% market share. Like, many people have never cooked on electric or induction. And so when you think of electric, maybe you're thinking of those electric coil stoves of dorm rooms or, you know, apartment living and things like that, which were not a great cooking experience. So I would say my answer to that would be, we do hear people love gas stoves, but I think that it's more people like what they're familiar with. And so the challenge for us is, what do we do? How do we get exposure and talk about all these other benefits of things like induction, where people may not be familiar with. And Rachel Carson, like the great environmentalist, had talked a lot about how sometimes the things that are in greatest risk are like in our plain sight. And so it's hard to imagine that this thing, the stove, your gas stove that you cook on all the time, may be harming you. So I think there's also like maybe the emotional barrier of realizing, you know, the stove, it's, you know, you start to side eye your stove after a while, but how do we make something familiar to us and start to realize that that actually could be posing our health a risk? And I think that's a secondary emotional barrier to address.
One very short example of that is that in studies where they have given people incentives to swap out a gas stove and induction, people almost uniformly choose to stick with the induction stove once they have it, to reinforce what Brady just said.
Great, thank you so much.
I'll jump in. This topic, maybe Brady, this is for you, but also Rob. You know, what is the evolution of the discussion with restaurants right now, where, you know, we've heard of some restaurants being very reluctant to move in the direction of induction and such, but we've also seen some restaurants embrace it. So I'm just curious, is that discussion evolving? Are restaurants sort of coming around, commercial chefs and such?
Sure, happy to start. And Rob, feel free to jump in. I think this is a little bit along the lines of like, you like what you know. And so even for some chefs, some culinary training does include induction, but many chefs or people working in the restaurant industry are used to gas. And if you are replacing, you know, we talk about like for like replacements. If something goes wrong and you need to change out a piece of your equipment, it's easier to replace gas with gas. So I do feel like there's less familiarity with induction cooking here in the US than other countries, where tons of Michelin-starred restaurants across Europe, Hong Kong, are already cooking with induction. Same thing with Australia. It's a lot less here in the US, and the Great British Bake Off is a perfect example of cooking and baking using induction. So I think that in the US, we have a bit more familiarity with gas, and that can be scary to switch, especially if you haven't cooked on that before. I do think that there's also something where electrification has become political, gas stoves have become political, and so there's part of associations that are aligning with certain industry interests. So unfortunately, with what happened in California and the Ninth Circuit is unfortunate, but I don't think that will change the pace of speed at which we do see policies switching to all electric. And I saw a New York Times article about how the future of pizzas in New York are actually electric and induction. And so I think that it's the natural evolution of things. And there's a chef Chris Galarza, who always says, you know, it's such an insult to chefs when they say that chefs can only cook on a flame. Because if you're a great chef, of course you'll be able to cook on a magnet. And so we've seen through history this evolution of going from wood and the open flame to gas. And I think it's natural for us now to use the technology and the tools we have, which are going to be climate aligned. Lots of chefs are interested in this, are going to be healthier, and also, quite frankly, going to be a lot cooler in the kitchen for your restaurant workers. So my answer, I suppose, would be a little bit of, it's hard when we're familiar with gas. It's going to take some time, but I do think the momentum is still pushing us. And we're lucky because induction is just a better technology. We didn't even talk about energy efficiency. Maybe that's not as sexy as the health, but actually induction stoves are super efficient, like 85, 90% compared to 35-ish% of a gas stove. So you're actually potentially saving money depending on where your electricity is coming from on your bills, and you're saving time.
Maybe if it's okay, Peter, I'll just jump in briefly. And we are beginning
Please.
to work with chefs in commercial kitchens, and our colleagues at PSE are doing the same. You have to think about a kitchen where you might have 6 or 8 stoves, where someone walks in the morning and turns each of those burners on when they walk in, and they're on all day long. Unlike homes, commercial kitchens do have a lot of pilot lights. Most of the stoves we see have pilot lights. So I think that restaurant workers may be more at risk even than homeowners. Now restaurants typically have better hoods, better ventilation systems. Our kitchens at Stanford have excellent ventilation, but imagine a kitchen in the basement of some small restaurant in San Francisco, and you might have workers not making much money, standing over in a small room with with 6 or 8 or 10 stoves all running at the same time. I do think we're underestimating the risks for people and exposure in commercial kitchens.